All right, thank you. So first I should start with a disclaimer. So whatever I'm talking about today is definitely not my idea or anything with this. It's all based on HWZ, and I'm just working it out, and Chris is actually helping me a lot with that. So all the mistakes are due to them, and I had all the ideas, or something like that. So in fact, the only good idea I think I had about polyfolds is that I should learn about them. The other thing I should say is I will say very few things about SC smoothness, because it's a technical point. SC smoothness is, well, something everybody has to learn eventually, I'm sure, and we just have to get to the stage where we just look at maps and say, yeah, that's SC smooth, as you do with smooth maps. And so I don't want to spend time on that. Okay, so that said, so I wanted to just explain the simplest possible, actually, I think, can think of example, which has a certain relevance to Morse theory, which is, I want to look at three distinct points in Rn. So we have A, B, C in Rn, mutually distinct. And then I want to look at the space of curves connecting, so if this is A, B, C, connecting A and C, A and B, or B and C. Okay, that's the space, and I want to just explain to you what you have to do to put an M-Polyfold structure on that space. So number one is so this is, of course, you see that has something to do with Morse theory, but there's no Morse theory at all. There's no Morse function, nothing. There's no gradient flow lines, nothing. It's just a space of maps. So, and to start with, one of the components certainly is curves between 2 points. So we start with that space, and I explain a little bit what you have to do there and what kind of structure you get. The one thing I want to do is, beyond what Katrin did, is I want to incorporate the R shift. So I want to divide out the action here and tell you a little bit why that, or what you have to do about that. Okay, so let's start with the easy space. I want to define a space. Well, first of all, just to really be precise, let's pick a map. There's any smooth reference map, so that f of s is A for s, say, less or equal than -1. F of s is B for s larger than plus 1. Okay, so we just have fixed the reference path and then define the space x hat AB to be, well, I just take H2 plus M delta M Rn. And do it like that. So M here, in fact, let's put an M here, and M ranges from 0, 1, Delta is one of these sequences Katrin mentioned. So delta 0 is 0, and then you take a strictly increasing sequence, and that's all I require for now. So I start with H2. Well, why not? Not H1. And then you can check. So this is, in a sense, even though it was never defined, a fine space, if you want. In other words, this is a scale Banner space. Okay, so you certainly see that there is a nested sequence, which is for higher m. So the space with index m plus 1 sits in the space with index m, and the embedding are compact, and that's precisely where you need these weights. So these are weighted Sobolev spaces. And, well, it's just an exercise in functional analysis to prove that the embeddings are compact. The only thing I want to mention really quick, so if you don't put weights, what you can do is you can take a little package here and send that off to infinity. The norm doesn't change if you don't put weights, because the norms are invariant under shifts. So you find a sequence with bounded norm, and now you put it into one less regular space, you don't get a convergent subsequence. This thing just goes off to infinity, right? So, but if you put a little weight here, so things have to decrease at infinity, you can't just do that. That's basically the idea behind these weights, okay? And you figure out the rest. Okay. So, yeah. Which weights? This here? It's precisely what Katrin used in the talk. So these are H2 plus M maps such that if you multiplied with e to the delta ms, it's still, oh, sorry, maps which are like this. Okay? So they're H2 plus m differentiability, but they decay at least as fast as this thing at infinity. Okay? Yeah. So the R action, this space carries an obvious R action. If you take a U in X hat, then and a tau in R, then you can act and that's precisely not smooth in any classical sense, but it is SC smooth. And yeah, as I said, I'm not going to say anything about SC smoothness. So this is a thing you have to understand anyway if you want to think about SC smoothness. But that you can check. All right. So then the space of interest is this one, the space without the hat, which is X hat modulus this R action. All right? And I want to study what kind of structure does this space have, and it is an M-Polyfold. In fact, this has even more structure, and we get to that. So number one, it's a metric space. This is a metric space. So we have on the spaces X hat, you have a metric D hat, the obvious metric, because you have it's a normed space. We just take the induced Banach's norm on the zero level. Zero level is just H2 maps. So this is the H2 norm, right? So this is important. I write the sublevel here, the subscript here corresponds to the level. This is not the L2 norm. This is, by definition, the H2 plus 0 delta 0 norm, which is H2. Okay, so there's already two derivatives involved in this derivative. Okay? But that metric is clearly R invariant. And then this space becomes a metric space with the property, with the definition on two equivalence classes, or actually I shouldn't write here, two equivalence classes. You just take, that's a standard construction, right? You take the minimal possible distance between representatives. And there's no head. Thanks. Okay, that's a definition. That's what you all would do with the quotient. On the quotient, you just take the minimal distance you can find. The point is, this actually is a metric. It's not so obvious because you take this infimum and it's complete. So this is very easy to prove. So that we don't. Well, I won't demonstrate. Actually, I want to write a little proposition here. It's not only a complete metric space, but on X, the metric and quotient topology agree. Yeah, so this you can either take the quotient topology, you can then take the induced metric topology, they agree. And the map, the projection map P from X hat to X is an open map. Okay, so this is the structure from a metric point of view. All right. So now we want to see if we can give this space X an M-Polyfold structure. So, well, as Katrin explained, I need to give you a local model of this space which looks like something in a splicing core. In fact, this has a better structure, so this will be, well, I'll tell you just what it is. And how? What?
How fixed is phi?
Like very fixed. There's one phi.
It doesn't matter.
Yeah, you choose
In this phi,
that little phi there.
first line phi,
I mean, is it the same?
Yeah, they are the same. Yeah, there's one phi. Just for once and for all, you choose a reference
just
path.
independent of short
Yeah, yes.
So I don't think there's the point in a tangent, the base of the tangent.
No, the point is, of course, these maps go to 0 at infinity. So if you want to go to A to B, you have to add on one reference curve. Yeah, That's the theorem. So you think of you fix one reference curve and everything else looks like an H2 curve over that. Okay. All right, now the details start sort of creeping in. So let me give you a lemma. So here's a lemma. So we have to deal with this R shifts here. And okay, let me just write it down. So for every sigma, we find a small epsilon such that for all maps H and K in H2 are n with, so they have to be small, epsilon small. So if you take two small sections, or two small H and K's here, such that, and it happens to be they are in the same equivalence class. Well, that means U plus H, V plus K. That means one of them is a shift of the other one. Yeah, they represent the same equivalence class. If that happens, U and V are fixed. Sorry, yep, X hat. So if you can write two equivalence, if you represent your equivalence classes in two different ways, but you know that you go away from sorry, not U and V. That's the same U, of course. So U is, I think of as a base point, and now I write two equivalence classes, one equivalence class in two different ways. But these offsets here, these H and K are small, then the time shift has to be also small. And here's the geometric picture you have in mind. So maybe this is U, and then you have something nearby, and you can realize it by two, and I think of H and K now as vector fields along here. So that means I can find a vector field maybe which looks like that. And another vector field which looks like this. Okay, so then one of these arrows is H, and this is K, and this time shift would be this one. Well, and if these things are small, then this thing is small. That's all the content there, okay? So this is very easy to prove. You just argue by contradiction. Okay.
But won't there be something at the end point that's a little different?
No, say again?
Well, I mean, you fix the end point.
Yes.
Now you're doing time shifts, so.
No. The time shift, you see, the time shifts, they always fix at the endpoints, right? So U is of the form phi plus some H2 map, and phi has compact support. So phi goes in finite time from A to B. And so if they shift that around, it still goes from A to B. Okay, well, okay. Yeah, maybe, then I don't erase the picture here. Okay. So now we need to read off from equivalence classes representatives in a nice way, and for that we use these transversal constraints. So this is a very general idea. In this case, it's fairly easy. So we just take a nice element U. So that means, say, in the infinity level. So just smooth for now. And I assume that it has to go from A to B. Well, at some point, the derivative better be non-zero. So let's assume U prime of 0 is non-zero. Okay, and then choose, at that point, a transversal slice, which means choose a hypersurface. So this is a linear hypersurface in Rn such that U prime of 0 plus sigma U is everything. This is your curve u. And then maybe this is u of 0. And then you have here u prime of 0. And you just take a complement in Rn. And of course, I mean, you shift everything to 0 then. So, okay. And then we can define domains for our prospective charts. So we define spaces W depending on our choice u, in fact also on sigma u, but definitely won't write that. They also get a scale structure M. These are all sections like over there. And I normalize them so that h of 0 now is in this space sigma u. That is W sub u m, and m runs as usual from 0 to infinity. And the top one I just write wu is w u0. Okay? And you just, I mean, it's not literally true, but these are basically Banach spaces. I mean, you just identify that with an Rn minus 1, and then that's it. Okay? You can think of them as Banach spaces. I don't want to, I mean, formally now you have to identify this with an open set and with a Banach space by identifying this with a fixed Rn, but that is yet another layer of notation which I won't introduce. Okay? So I want to use these things as chart domains. So, and I think of them as Banach space. Okay. Yeah. Yes. It is. Yes. Good. Yeah, but if you want to say how you make it a Banach space, then you maybe want to identify it with something. Yeah. Okay. This is just. Okay. Okay, so the idea is, well, here's my representative, well, here's one thing, and I pick this representative, so look at the class U, alpha, which is represented by U, and how do nearby classes look like? Well, these nearby things look sort of like that. So a nearby class has to intersect this hypersurface sigma U here somewhere, and that's the way I pick my representative. I just require the representative at time 0 to pass through that thing too. And to make that precise, we need the following little proposition. And I write it in two ways, which are trivial equivalent, but both have their advantages.
So at this point, you're going to use it to work in HT, not
Yeah, I need C1. I need a C. Yeah, so I have at least all the maps are at least C1, and so they have a first derivative. Indeed, yeah. So here's the proposition. The point is just basically just making precise what I just said. Nearby things go through there, and I can pick everything nicely. So we fix U and sigma U and everything. So then the first kind of stating is. There exists an epsilon 0, there exists a delta 0, such that all maps W close to U, and close to U is I just write in the metric sense. So this is here the delta hat ball. Here this space I just erased it, so our space X hat. These were phi plus h. That was a metric space. So just take the ball, meaning these maps are epsilon 0 close in the H2 norm. There exists a unique time shift, tau u of W in minus delta 0, and there exists a unique vector field, such an H along U, which also depends on W, in our space WU. Well, such that if you have to shift W by this amount tau of W, then you can write it as U plus H of W. Okay? And that's just saying precisely what I said before. Nearby curves, after shifting them, you can write them as u plus something which is normalized in sigma u. Okay? So what does it make? So the uniqueness comes from two things. First of all, the uniqueness comes from this equation and the requirement that that thing is close to 0. Yeah, so the normalization, if you want, is tau u of u is 0. And then all I'm doing here is an implicit function theorem. Yeah, this is sort of what, this is really just an implicit function theorem. So let me add one thing here. The maps u goes to, w goes to tau u of w. This is a map from our space, from our scale space x hat to the reals, which are trivially a scale space by taking the scale r. This is SC smooth. And w maps to h of w also. In fact, this one follows from that one because
But we don't have a smooth structure on X hat yet.
x hat is not the quotient. X hat is the parametrized ones. They are an SC space. Yes. So if tau is smooth, then h is smooth because h is just this minus that. Okay. So this is the one point where I want to say a little bit about ST smoothness. So I'll maybe do that over here. And all I'm doing is here's a proposition from HWZ. In fact, the first paper on polyfolds. If you have a map on a scale space with values in R, and you know that, well, you assume it's SC0, okay, such that if you're on level M, then the map is in fact, in the classical sense, Cm plus 1. Then F is C and SC infinity. And now you just set up the implicit function theorem for this proposition in whatever way you want. And then you just realize it has precisely this property. And that's how you get SC smoothness. And this is in fact too strong. I mean, this implies SC smooth, but is I think strictly stronger than F being SC smooth. So it's not that if S is SC smooth, it has this property. Yeah. Mm-hmm.
I'm so confused about that.
Sure.
I'm so confused about that.
Yeah.
I mean, you set the values of the endpoints to be the points, and I don't see that you have, I mean, I'm sorry I came in late.
Sure.
I don't see where the shift now preserves the boundary.
Okay. So any map U here is of the form phi plus h. Phi is a curve like that from A to B, but phi of
And I think it's crucial to say that those are not boundary conditions, they're limit conditions.
yes.
Oh.
There's not finite curves. They're defined on R, right?
Oh, I'm sorry. I missed. They were just limiting conditions
At minus infinity, at limit.
Sorry.
Okay.
To interrupt, but I
No.
really, the automatic thing to do is to thinking of them as boundary.
No, they're limits. They're limits. I see. Okay.
Okay, thank you.
Okay, very good. All right. So in fact, that is the only proposition I basically need today. And well, you can prove it or not. But then you get this proposition, and I wanted to give you an equivalent version of this. Yeah. Say again? Two things give me uniqueness. The first uniqueness is, I mean, the normalization is tau u of u is 0, and this equation. And these two things make it unique if you require tau u to be sufficiently small. Yeah, of course, if you don't make tau u sufficiently small, well, you can have nearby curves can of course look like that. Yeah, and then you have more than, I mean, there's not a unique point where you hit sigma u, but if you assume that everything is close by and you don't want to shift too much, then it becomes unique.
Right, close by in C1.
Close by in C1. Indeed, yes. Right. And then if you look at the...
So somehow here you're implicitly assuming assuming that there's a Morse function in the picture and
No.
the functions go down. No, but otherwise they could loop around a couple of times.
Yeah, fine. Doesn't matter.
But then your intersection point would be unique.
What would be unique?
Oh, you're asking the intersection.
No, I'm not saying the intersection point is
You're
unique.
not saying that the intersection of sigma is unique, you're saying the intersection near zero. Right.
Yes.
Yeah.
Right.
It's in the C1 norm.
Yes. Yeah, so there's tons of places where one can confuse oneself. Okay, so the equivalent version is it's very similar. Just want to write it down anyway. The equivalent version is you don't phrase it in terms of W, but in terms of the vector fields here. So they exist in epsilon and they exist in delta, such that for all k in H, 2 plus m delta m which are sufficiently small, there exists a unique tau u now of k in minus delta 0, such that tau u of k star u plus k at 0 is in u of 0 plus sigma u. It's really exactly the same statement, just in sort of a different geometric setup, in a way, if you want, or a slightly different phrase. So I'm just wondering if you take everything sufficiently small, and I'm looking at the map I get by taking u plus k. That, of course, won't intersect at 0 the constraint anymore. The question is, how much do I have to shift it? And I again can find under smallness conditions a unique shift who does this. Okay? And the translation from there to there is W is u plus k, and the other way around is k is w minus u or something like that. So they are totally equivalent. I mean, it's a one line. Okay? I don't know. There are different ways of thinking about the same statement. Okay? All right, so finally we can write down a chart here, or an attempt of a chart, which will be the following thing. Make a definition. We define a map psi u on W epsilon to X. X is our space, X hat AB mod R. So WU, is it still there somewhere? So WU was the space of H for which H of 0 was in sigma u. And then if I put an epsilon here, then I also require that they're small. The 0 norm is smaller than epsilon. It's just of the epsilon ball in this Banach space. And the map you do here is just take an H and map it to U plus H and take the equivalence class. That's not a chart. I think it's a local parameterization. I don't know, whichever way it goes. All right. And to prove that that is a chart, well, this theorem tells you, or this proposition tells you, basically it's surjective locally. Where come all these pictures from?
That's Arnold diffusion.
I see. I see colors. So that this is locally surjective is this proposition. The theorem is, indeed, they serve as local parameterization. So this theorem is for epsilon sufficiently small. These maps psi u are, first of all, continuous, injective, and open. Yeah, in particular, the homeomorphism on the image. Okay? And so continuity is actually fairly easy. Well, it's easy. It's the map H goes to U plus H is continuous, and taking the projection, which is taking equivalence class, was continuous too. There was a remark earlier, so continuous is for free. So let me explain to you how to, oh, and erase precisely the lemma I use now. Great. And let me tell you how to prove injectivity. So now we assume that H and K go to the same thing. That means we assume we can write the same equivalence classes like this for H and K in this space W U epsilon. Since they're the same equivalence class, that means one of them is a shift of the other. Okay? So this implies that if you now evaluate the left-hand side at 0, this is u of tau plus h of tau is equal to u of 0 plus k of 0. So this is in u of 0 plus sigma u by definition, because well, k of 0 was in this space. No, this is a space. Okay. So now there was this lemma: if you find two shifts which are the same, and all the ingredients are small, then that was the lemma I just erased. This shift has to be small. Yeah. So if you make two different moves from the same curve, and the moves are small, these two little vector fields are small, then the shift from one to the other has to be small. So that from the lemma, no, this thing is small. So then from the proposition, we know if this tau is small, well, then there's a unique tau. So I know this tau has to be tau u of h in that language. Okay, so I use the lemma to conclude, well, the shift can't be too big. And I'll use the proposition to conclude, well, there's precisely one shift, so it has to be this tau u of h from the theorem. Okay. Well, and now we're done. Because we also, why are we done again? So tau u, right. So now you just look at u of 0. Now I'm going to.
U plus h at 0 intersects at 0, and that's a locally unique point.
H of 0 is yeah, right. So u of 0 plus h of 0 is trivially in u of 0 plus sigma u again. Okay, this is just by definition of this being in this wu, and this tells you, well, if there's any shift like this, then again by uniqueness tells you tau u of h is 0. These things you don't have to shift already. They intersect the transversal constraint where they have to, so the shift is 0, and then the things are the same. Okay. Well, this is the kind of arguments you run through roughly a billion times. So what remains to prove is openness, and that is billion minus 1. So there you use it again and again and again. The same kind of arguments I'm not going to show you. Okay, well, I just wanted to illustrate what kind of arguments you encounter here. Okay, so in short, we proved the theorem, sort of. So in particular, we can locally parameterize our space by open set in the Banach space. That's better than what we need for an M-Polyfold, but certainly good enough. Okay, yeah?
Sorry, again, there's somewhere in this argument, there's a very important fact that you've got decay, so you don't have things that look periodic, right?
Yes.
I mean, it isn't just a question of CK, I mean, or C, whatever.
Mm-hmm.
You actually really need the decay so you don't have stuff that looks periodic, right?
Not quite sure I use that here already. I'm definitely going to use that.
No, if you have on the lines periodic functions, bounded functions only, that wouldn't really work.
You're going from A to B, where A is not equal to B.
Right, no, I know.
I mean, the problem would already be if you have the same limits right and left. I think you would already have an issue with the CR actually.
Yes, that is true, because then this lemma is not true anymore. Yes. Yeah. No, Karen is right. You know, you're right. In fact, in this lemma here, which
right, the lemma
yeah,
that you erased.
this lemma, yes, indeed, that uses the fact that A and B are different, and that you yeah, you're right. Because in fact, if you go through the proof of that lemma, you prove by contradiction, and then you produce a periodic function which goes from A to B.
Yes, okay.
So if that thing is periodic, that yeah, okay.
It's also not an H.
Yeah, that's also a little bit of a problem, yes. Okay, so we have our candidate for the local parameterization of our space X. So now all I have to make sure is that that chart changes or coordinate changes are SC smooth, and that is indeed the case. And I'll just write that down for you. So there's not so many things to change here. You have just one kind of chart. So the theorem here is that if you take a psi u0, and then you go back with a psi u1 on whatever appropriate domain, this takes an h, maps h to the equivalence class u plus h, and then somehow goes back. We know it's invertible. And you can, while you sit down and compute this, locally this looks as follows. Okay, it's not pretty, but it's straightforward to derive that. Right? So the map locally, this map looks like you send h0 to, well, first you compute u0 plus h0 minus u1. That is a k in one of these propositions, so that has a t of u1, a shift. And then you shift this map u0 plus h by that amount and subtract u1. That's it. And all you have to do is you have to check that if you apply that map to that expression, you get the same equivalence class as u plus h0, u0 plus h0. That's very straightforward to derive that. Once you have all proved all that stuff, you see, well, this is certainly SC smooth, because I told you this map is SC smooth. The shift operator is SC smooth, and then you subtract and add and so on. That's it. So it's SC smooth, and that's the end of the proof. So this implies this X space, which is X hat mod R, is, in fact, according to HWZ language, an SC manifold. That is not entirely proved by this. You need some topological assumption for that, but you can check that too. Okay? So this space is actually very easy, but it's of course not the space we want to consider really, right? This is all this curves from A to B. What we want is curves from A to B, A to C, and B to C. And so that will be then an honest M-Polyfold, because you can't do it with one kind of chart. All right. So this was sort of the warm-up exercise. So now let's fix the setup for the real M-Polyfold. So our space now is fancy X, which is just, well, you go from A to C, and you take pairs from A to B and B to C, and there are no hats here, so these are all quotient out by the R action. And so far this is a space, doesn't even have a topology. The first step will be give this space a topology, then we understand the topology a little bit, and then we can talk about what local charts should be. So we want to define again something which is continuous, injective, and open. Now we need two kinds, something which takes care of this part, and then something which takes care of this part. And then we have to prove, well, everything fits together nicely. All right? So actually the first big step is the topology. So for that I want to just recall what Katrin mentioned briefly in a talk, also since I have slightly different notation as of, this gluing and anti-gluing. Okay, so for once and for all, we fix the cutoff function, theta. This is just a smooth function. What are the properties? I want theta of s is equal to 1 for s is less or equal than minus 1. Theta of s is equal to 0 for s greater or equal than 1. Theta prime of s is less or equal than 0. And the last thing I want, theta of minus s is equal to 1 minus theta of s. Okay, so in other words, I want a function which looks like this. I have 1 here, 1 here, minus 1 here, and the function looks like this. Oof, yeah, well, more or less. And the point is sort of symmetric if you flip it and flip it. That is this 1 minus thingy there. Okay, so in particular, this point here is 1/2. This is the graph of theta. Okay. This is just for normalization, but there you have it. And then for the rest of the talk, I will have to shift maps around. So just notations, if I put a subscript to a map, then it's the map shifted like that. So for theta, for our u's, so u r of s is u of s minus r, etc. Okay, if we have that, we can define plus and minus gluing. And the plus gluing is a natural operation. You just interpolate between two maps with help of a cutoff function. So the plus gluing is something very simple. So we fix for now r will always be larger or equal than 0. And then the plus gluing, denoted by that, depends on this r, takes two maps, gives you a map. So we'll say it takes two continuous maps, gives you a continuous map. So it takes two maps, u and v. And for now, it doesn't matter from where to where they go. And this is just the formula you take. Theta shifted by r over 2 times the map u. And then you add 1 minus theta times the map v, but shifted by r. Just multiply this. So you have, I don't even know how to, you take u, whatever your map u is, and you take, I'm not going to draw a picture. It's just a standard interpolation formula from one map to the other. The only thing to remember is we shift, the second one we shift by r. Okay? The only important property you want to remember about this map for later is that if you take the plus gluing and you evaluate it as, then it's just the map u of s. Well, whenever this is 1 and that is 0, that happens exactly at, well, at least if s is less than r over 2 minus 1, because we shift this thing by r over 2. And the other thing it is, it's v sub r, so it's v of s minus r when s is larger than r over 2 plus 1. So there's this region sort of width 2, in which you don't know exactly, but other than that, you understand this map. Okay. This is geometrically just interpolating between two maps. And it has this companion thing, which Katrin gave a very nice visualization of this morning, which is the minus gluing, which for our purposes just complement that map so that together they form an isomorphism. So let me just write this down too. So you take u, minus gluing of u and v is just the complementary thing. Oh, yep.
Is this a different notation for your bump function and your antiglue?
No. Yeah, that's bad, right? But one is this theta, one is an O minus. Yeah, that looks very different when I write it. Yeah, you're right. Oh boy.
O minus would have a r.
Yeah, the thetas are gone very soon. Okay, so the thetas look like this. I apologize. If I start changing notation now, and then you get a random perturbation in a minute. Okay, yeah. LaTeX does wonders if you type that. The point is you can write plus r uv minus r uv, if you think of it as a vector of two functions, just put them together, as the matrix, which is theta r over 2, 1 minus theta r over 2 minus 1 minus theta r over 2, and theta r over 2 times u and the shifted v. And as Katrin pointed out, if you compute the determinant of this matrix here, it is theta r over 2 squared plus 1 minus theta r over 2 squared, and this is always positive at each point. It's just a little computation you make, and thus this matrix is invertible, and thus these operations together are an isomorphism. And this thing together I want to call dot. LaTeX box dot box, I don't know, of uv is plus r uv minus r uv. And So for me, these maps are always defined on R. So as different from Katrin's talk this morning, this is really now a map from one and the same space twice to itself. It's an isomorphism, and E is this H2M plus H2M, H2 plus M delta M space. Okay. So it's not only an isomorphism, you have estimates of the form you also have an injectivity estimate.
In fact, there's a CM for every M.
Yeah, there's in fact a CM, so this is SC smooth, but the injectivity estimate, unfortunately, becomes a little bit, yeah. This is all I need for now. So you have these two standard estimates, this injectivity estimate and so on. Okay. And we're going to use these operators to define our topology on this space X. So, well, we have to, yep.
You haven't defined anything for R equals infinity.
Oh, I haven't defined anything for I equals infinity. Well, as in Katrin's talk, it's the identity. So theta infinity of uv is uv, and the same with minus. Okay. Well, oh, whoa, that's nonsense. No, I shouldn't do that. These get one map, so I shouldn't. No, I don't really. What I meant to write is this: dot infinity. That's all I need.
And then also there's this thing that I think only more out by the R actually gets a good map, because you have this U and the V flies away. The S
No, for now it's just a definition. I'm not saying it's anything in R yet. The point is this map sucks in R. It's really not good. It's only if you see later what the right map to look at is. Okay, so
Oh, but in order to talk about the infinity, you're going to need to talk about topology or something.
say again.
Well, to get the infinity.
No, this is just a definition. I'm not saying it converges in any sense. This is just a definition. Okay? And as I said, this map doesn't behave well in this R. A combination of maps will behave nicely in R. This is just, in R this doesn't converge to anything nice. Okay, so finally we can define the topology. So, well, we have two types of elements in our space X. One is a gamma, which is in, say, XAC, and then there's a pair in the other. And I want to start with the neighborhood of this. So we have two types of neighborhoods. Type 1 neighborhood is around an equivalence class like that. And on this piece, we just take the induced topology. So this is this space already has a topology from previous part. Right? This is in fact a metric space, so we just take here the epsilon ball. So that's the first type. So in particular, as a subspace, this thing has just its own topology. Much more interesting is the topology around an alpha beta in XAB XBC. So first of all, I take representatives, so you say U0, V0. Yes. So this sits in alpha, this sits in beta. And I need an epsilon 0 and an R0. And then, well, so what should it be? I mean, you have this is a configuration like that. You go from A to B with U0, you go from B to C with V0, and then we know what should be nearby. Well, something like that should be nearby, but also something like that should be nearby. Okay? And formally that just means we just plus glue whatever we can do, U0 plus H, V0 plus K, and we have to take equivalence classes, because these are spaces of equivalence classes. And then H is small, K is small, and R is large. And the convention now is plus infinity of UV is UV. Okay? That's it. These are our two types of neighborhoods. And I'm saying, well, now take all possible combination of that, and that defines a topology. And that's in fact a theorem, which is not so easy to prove. We can write here. So the theorem is, if you take the collection of all these guys, so for whatever there's around, yeah, for all epsilon, for all gamma, for all equivalence classes alpha, beta, and representatives albetas, for all R. So for all whatever you have to can choose here. Forms. Yeah, forms a basis of a topology on X. That's the first thing, which is fairly difficult to prove. Then the topology is second countable. This is not so surprising. I mean, you do the usual thing. You picked everything sort of rational.
Actually,
yeah.
Already it's clear by that first statement that the non-broken path is already open. And then
Yeah, I'll come to that. Thanks for the souffleur. What's that in English? Okay, so it's second countable. That's easy. That it's Hausdorff is not so obvious. So this is a Hausdorff topology. Then, furthermore, on XAC, on the unbroken stuff, the topology is the old one. So it agrees with the metric topology on that space. And finally, XAC is open and dense in this space. So if you take the closure of the unbroken stuff, you get everything. Okay. So that takes, in writing, 5 pages and is not pretty. So have fun with that. It's topology. What? It's the only ingredients you need is I just erased it. No, it's still here. The injectivity estimates and so on. That's all you need. And then you can just have fun with these numbers. Oh yeah, and this implicit function theorem lemma another 5 billion times. Okay, so now we have a topology. And I want to say one more thing about the topology, because it satisfies the obvious thing you would want to have, namely that things converge in the right sense. So meaning if you have two sequences, un converging to u, vn converging to v, and then you can look at sequences of this form. You glue u and vn with the parameter r and then take the equivalence class. And then you try to understand what the limit is of this. So there's two choices. Well, if the rn's converge to infinity, then this should converge to the broken uv, and that's the case. Of course, if you take equivalence classes. And if the rn's converge, well, then you also get the thing you expect. Okay, right? This is convergent, and we have a topology. You can write down what convergence means. It does the right thing. Okay. So now we have a topology. It has the right properties there. Now we want to construct charts, and now we need to think a little bit. So if you have such a guy here, so such a W here, going from A to C, then nearby things are certainly also unbroken. So they stay entirely in this set XAC. That thing has its old topology, and we know how the local models look like. That was the previous thing. So on near these things, we know what to do. Take the old charts. That is already an M-Polyfold, even an SC manifold. Just take the charts you have. It's an open subset of a manifold, sort of, yeah? The only question is, what do we do with things like this? So we know how nearby curves look like, and then we need to go get nearby nearby charts. The idea here was to say, well, I have these local constraints, sigma w, and then this was w of 0 here. Well, you have, so to be able to read off nearby things, you have the same idea for things like, for things here, u and v. Well, you want to read off, in particular, things which look like that. So we need two transversal constraints, sigma u and sigma v. And then you try to build up charts out of that. Okay? And you see that already becomes a little bit more complicated. All right, let me tell you what you have to do. It's not that much, in fact. Yeah, okay. Let me skip this lemma here. So I just first tell you what the chart domains are. So my chart domains are now u1 hat and u2 hat. Or actually domains for local parameterization, and the one is again corresponding to the open sets here near these guys and so on. So this is very easy. Near an unbroken one, we take the old ones. Well, the old ones were in this case these spaces w, w0, epsilon. So all h sections along w0 with h of 0 in this transversal constraint, and in norm less than epsilon. Old chart domains, and we take also the old parameterization. So what is the new one? Well, you have to go near, fix the center of the chart, u of 0 and v0, where we fix an epsilon and r0. Okay, this will be an r, an h, and an k in, well, okay, in r0 infinity. So r is just bigger than r0. The h is in the corresponding w space for u0. And the k is in the corresponding w space of v0. Yeah, so just think of one of them as a vector. You have one vector field here, and you have one vector field here. Okay? Of course, we also want to get these guys nearby. They also are close by. So those are certainly not given by two vector fields along u and v. And you see in a second how we remedy that. So I need to add a condition here. So this would be fine if you would just take the product thing. But what is the r for? Well, and this is for now mysterious. The minus gluing of h and k with this r has to be 0. And you're not supposed to understand that on the nose. Okay, I'll explain in a second why that is the right thing to do. Okay? Maybe it's a good idea that I tell you first how you make charts out of that. And I can do that here. So if you believe me for the second that are the right chart domains, then I can tell you what the charts are. It's actually fairly easy. You have a type 1 chart around W0. And as I said, this is the old one. So an L here goes to W0 plus L equivalence class. That's the thing we had to do before. Boring. The new one is okay. The new one is the following. Well, we take an R and an H and an K, and we just glue the shifted things with parameter R. And again, the notation is if R is infinity, is just you just forget about the gluing. These are the maps. Okay. And now we want to prove the same lemma. For this one, we already know it's continuous, injective, and open. For this one, well, we have to prove the same thing. But then remember the definition of Katrin gave to you is that things have to be defined in open sets of splicing cores. Okay, so this is just an open set of a Banach space. Fine. So the question is, which I want to tell you first now about, is why is this actually an open set in one of these splicing cores? Because otherwise we're defining here something, well, that's part of the definition of an M-Polyfold. You have to find an open set of a splicing core, and then a homeomorphism, which this guy will be, into your space. Okay, so question is, why is that actually an open set in the splicing core? And even though Katrin doesn't like it too much, I use this retraction business instead of splicing, but it is really a splicing here. Okay, so a statement is lemma this U2 hat with all this decoration is an open set in a splicing core. Okay.
At that point, you should have chosen a gluing profile.
No. Yeah. You see, that's the part of where I said I'm not talking about SC smoothness. If I want to talk about SC smoothness, I have to tell you what I do at infinity about differentiability. For that, I have to use a gluing profile. And
R equals
infinity, yes. So I can't tell you what smoothness at infinity means properly. If you want to do that, then you have to translate something of the form 1 infinity into 0, Katrin, I think, used 1/2. And that's where you use the gluing profile. And then you can talk about SC smoothness as 0, which corresponds to infinity. Since I'm not talking about that, I don't want to talk about the gluing profile because it adds yet another letter to all the complication here. Yeah, I tell you that there is a projection, and if you put in the gluing profile, then you get everything. Okay, the boss is happy. So, why is that true? So first, note the following things. Our condition, this funny condition down there, the minus gluing of R, the minus R gluing of H and K is 0. I can just rephrase with help of my box operator here. It's the same thing as box R. Remember, box R was just plus R, comma, minus R. So if I take box R of HK, well, then I have no idea what the first entry is, so I'll just write it. That's the first entry of box. The second entry is minus. Okay? So it's a tautological statement here. Box is plus R minus R. And if I write this equality, it just means minus R is 0. Okay? Totally tautological. And it keeps being tautological. That's why probably I mess up the proof. Yeah.
Sorry to interrupt. So
Yeah.
over here, the U2.
Yeah.
So I can get them. So how do I think of so at a point RHK, I think of gluing a parameter R, the tuple RHK. I think of H and K are vector fields over the broken
Yes.
guys. I sort of glued in the parameter R.
Yeah.
And then the condition that is.
The condition is the magic
I can glue them or
No. This I'll explain now, why that is actually important. Okay? All right, this is what I'm going to explain now. This makes it into an open set in the splicing core, on which the map is injective. This phi2 map is injective. Yes. So number one is, if I drop this condition, then it's just an open set of a Banach space. Actually, it's a product of 3 Banach spaces. Well, that's fine. That's an open set in the splicing core. Problem is, this map is not injective then. So if I want to make it injective, I need to add a condition, and precisely that is the condition I need to add to make this map injective. And then the question is, why is it an open set in the splicing core? And for that, I have to rephrase this condition slightly. Yeah.
So there, you also allow R to be infinity.
Yes, and
R0 infinity.
and infinity just means h comma k is equal to 0. Yeah.
No.
What?
No condition.
Sorry, it's minus. Minus infinity of h comma k means no condition, right? Thanks. For plus, it would be just h. Okay. Okay. So my claim is yes, right. So that means I can rewrite my type 2 neighborhood as follows. No, not my type 2 neighborhood, but this U2 hat as these are all the RHKs for which, well, h comma k is the same as, well, you just take this equality and put this guy on the other side. So box dot R inverse of plus RHK comma 0 That's it. Yeah? Well, this is the condition I wrote initially. Well, then this is equivalent to this condition, and you just take this invertible thing on the other side, and you get this equality. Okay, just keep on rephrasing. And then now we see now we see a retraction, right? This you can think of, well, you take h and k and map it to, whoa, this hell of an expression here, and you get back h and k. That is precisely the being in the image. That is precisely saying h and k is in the image of this map, of this projection. Okay? So my claim is that box.r inverse of plus r, actually I should write it like this, h comma k maps to box.r inverse of plus r h k comma 0, that this map, that is an SC smooth retraction. Yeah. Very true. If I really want to talk about a retraction, it's the map RHK maps to R comma is and this, as I said, this SC smoothness, I'm not talking about retraction. So, and as I said before, the map box R itself at R is not nice if R goes to infinity. It doesn't make much sense. But this expression together is very nice. It's actually SC smooth if you put in here now the gluing profile to make the R's into parameters going from 0 to 1. Okay? And this converges nicely, as you can convince yourself. So I just want to prove it's a retraction for you. It's just because it's basically tautological. So let's see if I survive this symbol war here. Okay, so we claim that that is a retraction. So that means, so let me drop this R here, right? That R goes to R is the retraction, is sort of clear. So I want to apply this map. H goes to this here. HK goes to this here twice. Well, let's apply it again. Oh God. Yeah, as I say, this is 1, 2, 3, 4, 1, 2, 3. At least the brackets are right. So if you write it twice, that's what it is. Okay. So so H hat K hat is the image. So if I write it like, if I abbreviate the image by H hat K hat, then what I really have to prove is so if I apply it to something which is in the image, it's actually the identity. So let me not look at the nodes. Let's see if we can do that. So first of all, let's put this on the other side. So now this is an equivalent statement. Okay, so this is what we have to, this has to be true. Well, this is just plus gluing comma minus gluing. So that the plus gluing is equal to the plus gluing is an empty statement. So this is equivalent to the fact that, well, 0 is equal to the minus gluing of H hat K hat. Okay, no, but H hat K hat is of this form. So let's put the dot R here. And so this is again plus comma minus. So minus glue of H hat K hat is indeed 0. So this condition is in fact true. And thus this is true, and thus you get this fantastic equality. Okay? So the right retraction in the background is not this dot plus R whatever, it's this magic combination of dot R inverse applied to plus R comma 0. That's the way it is. Okay.
Say that again.
So the retraction is neither this dot box R plus R minus R, any of that. The retraction the retraction rho of RHK is this combination. Well, you have to remember the R is this combination. You have to take R dot box inverse applied to plus R comma second entry 0. That happens to be a retraction.
I must confess that I followed everything line
That's all right. No.
Actually, if you have plus minus, if the plus gluing and the minus gluing itself, the pair, is an isomorphism,
Yes.
and you put 1, 0, there is a unique projection onto the 1.
Which is this?
Which is this? That is actually without formula.
Yeah. I mean, you can also try to think about it geometrically. Oh God. So your point is you have an isomorph.
Suppose you have a Banach space and
Yes.
you have a pair of maps to another. To a
Yes,
product
you have
space,
E cross E to
which is
E.
an isomorphism.
Right.
Then you-
Then you write this as this is an isomorphism which has two components. And then you can look at the kernel of either of them. And then you have a natural projections in terms of the other map onto this kernel. And this, if you now write everything else, is precisely of something like that.
So you don't really know too much about what it looks like.
Oh yes, you know.
Yeah, well, in the end, it's precisely given by this condition.
No, you write it down.
Oh, you mean how this image looked like? Yeah, we can write it out. I mean, it's not nice, but it's explicit. If I'm not quite sure how much it buys you.
Somehow not nice.
No, it's not actually so bad. It's just. You
Well, he has
write-
funny standards about bad.
It's some multiplication by some cutoff function times u plus a perturbation of another cutoff function with some shift of the other. So you can actually
Not so bad.
You can reduce this thing to some standard. There's a standard lemma which says the following list of things on this standard rules, and you can write it this way.
Yeah, oh, by the way, if you want to learn about SC smoothness, there's a very nice paper by HWZ, which is 125 pages, basically starts with the following set of maps is smooth, SC smooth. So if you want to know SC smoothness, you look it up there. And everything I'm using today there is in fact in there, one way or the other. Well, it's that paper.
Has SC smoothness in the time.
It's in Journal of Modern Dynamics. It's in the Louis Nierenberg 80th birthday, 85th birthday volume. I think it's Journal of Modern Dynamics. 125 pages. Everything's SC smooth.
So what's the author?
Second,
The author?
HWZ, Hofer, Wysotsky, Zehnder. Yeah. Okay, so since we're already over time, I want to write one more statement and then at least give you an idea where this condition pops up, and then we're done. So the last thing to prove is this map. Where is it? Oh, it's probably long gone. This map, phi 2, what did I call that actually? Phi 2 of RHK, which is, take the plus gluing U0 plus H, V0 plus K, equivalence class. This is continuous, injective, and open. Continuous is again for free, if you understand the topology. And I want to just briefly tell you how to prove injectivity. And again, openness I'm not going to tell you, and then everybody can have a nice afternoon. All right, so let's prove injectivity. So if you assume we can write this also as R bar, H bar, K bar, well, then as usual, two equivalence classes are the same. So we find some, I think now it's a T, well, now T such that T star plus all the bar stuff is plus the unbar stuff. Okay. So if it's same, then up to a shift, and without loss of generality, you can assume that T is say negative. If not, put it on the other side. That took us a day to figure that one out. It wouldn't work. The proof wouldn't work with speech positive until you realize otherwise you put it on the other side. Anyway, I don't want to go through all the motions again. You use the fact that if you take S lesser or equal than 1/2 R0 minus 1, you know if you do that, then so R0, R bar and R are both larger than R0. So in particular, in this region, you know these plus constructions always give you the first entry. Okay? So you get again an equality of the form U0 plus H is equal to T star U0 of plus H bar is the same as U0 plus H. not for all s, but for a very large set of s, it's still enough to conclude by a similar lemma as before, this shift can't be too big, let's say less than delta. Okay, I'm being a little bit vaguer now, but there's a similar lemma as before. You can strengthen this lemma if you have two things which agree, and h bar and h are not too big, then you and they agree up to a shift, then the shift can't be big. Okay, first thing. Then you use the fact, now we tick off the conditions. So we use that these maps are small. Now I'm going to use that they are in these spaces. So now use that h and h bar are in W U0 of epsilon. And just redo what we did before to conclude t now is actually 0. Because you find twice a shift which at 0 and at t satisfies the transversal constraint, and that only happens if t is equal to 0. Same argument as for the single one. So it's a funny way of arguing. First you make t small, and then you conclude it's 0. Okay, but that's the way it goes. And
so yes, 0, and then you can use a transversal constraint.
Yes.
So you always have to focus.
Yes. So first you have to get them close, and that is this first step.
I'm just worried that h is 0 on a large set.
Fine.
It's okay.
But then you have U0.
Then the shift won't do anything.
Yes.
You can't conclude the size of the shift.
No. That's
No.
Okay, but go on.
no. The point is, then it has to be. This is for a very, very large set of s. It's almost entire, right? This R0 is I think of as very, very large. So if you think of what you think happens, then basically on the entire real line, and then eventually you get the right result, because these okay. So what you have to realize is A and B are a definite amount apart. So you can make sure that you know.
Somewhere h is that.
Yes, you have to go from one side to the other eventually, and you can't do that near infinity because then these maps are going to 0 very fast. Yeah. Okay. So and once t is 0, you have h is equal to h bar. Fine. So that's the first thing. Oh no, that's not true. Sorry, that's not true. Because if t, you only know that up to 1/2 r minus 1. So very far out, it could be still non-zero. It could be still different. Okay. But at least we got rid of the shift. So we have this equality now. And now we assume, say, r is larger or equal than r bar. If not, in this case, it actually works with both signs. So, well, then you do the same trick. Now you evaluate for s large. Namely, for 1/2, you look at the remaining bit. And then you get an equation of the form v. Then these expressions are just the second entries. You just get v0 of k of s is equal to v0. Sorry, these are shifted. Minus r is v0 plus k bar of s minus r bar for all these s. Okay, so well, then you put one on the other side. You shift the s around a little bit, so you get v0 plus k of s is v0 plus k bar of s plus r minus r bar for many s, for all s larger or equal than minus 1/2 r plus minus 1 or something like that, plus 1. Okay, but that's precisely the same situation again now, like here. For many s, for almost the entire real line, you have two shifted things agree. And k bar are in this W space, so we again conclude, well, this shift, which is now r minus r bar, has to be small. And then, again, you conclude they are the same. In this, by the transversal constraint. So this you conclude from a similar lemma, and then you use k and k bar are in the W v0 spaces. So we use this condition, we use this condition. Where do we use this condition? So the last thing we know is then plus r u0 plus h bar v0 plus k bar is plus, well, r bar is the same as r, I already used that, r of u0 plus h v0 plus k. And I want to know h is h bar, k is k bar. And now I can just add a line here. So first of all, these operations are linear. So you write that as minus r u0 v0 plus minus r h bar k bar. So then this line is true precisely because of this condition. Yeah? Because what I'm writing here is minus r u bar 0, u0 v0 is on both sides, that doesn't trivial. And then I have a minus r of h bar k bar, that is 0, and a minus r of hk, it's also 0. So I can write this line. And this just says box dot r of u0 plus h bar v0 plus k bar is box dot r of u0 plus h bar h v0 plus k. This is an isomorphism, and thus these entries are the same, and thus h bar is equal to h and k bar is equal to k, and I finally have the thing injective. And then you jump through similar hoops to get the thing open, and then you check transition maps. Then now we have many transition maps to check. You get expressions which are derived from implicit function theorems, but all of the same form. Shifts plus adding plus subtracting of things. So everything is SC smooth. This is really the crucial part, to get this local parameterization of the space. So if we put everything together, then at least this funny space X is indeed an M-Polyfold. Yeah, and then you have sort of the base.
Assuming not an SC manifold.
I wouldn't know how to prove that it's an SC
No,
manifold.
I wouldn't prove it either, but I don't think.
Yeah, first of all, it's completely unnecessary to know that, but I don't believe it's an SC manifold. So I think for this you really need to go to splicing course. Yeah, you can't deal with local models in Banach spaces anymore. Well, and that is sort of, well, this was with 3 points. Now if you want to do Morse theory, you have many of those. Well, then you keep iterating the construction. Then you have to put bundles over that. Well, and then you have to look at fractions, a long story from there, right? So, but this at least you see what you have to do in principle to at least give this the simplest possible space you can think of an M-Polyfold structure.
It turns out it's actually not that long anymore. So if you now if you do it with several points and several borders use the same. I mean,
Sure.
everything is here.
Yes.
So then
Bundles is the
then
same
you have to
story.
prove- then you yes. So then you just have to show that if you fix a certain number of points, you take a smooth map from Rn to Rm, which then maps these particular points to different points, pairwise. That this map then, for the same construction for the other Rm, is actually SC smooth.
Mm-hmm.
And then you can just take any manifold, you properly embed it,
Yes.
you take a tubular neighborhood, it defines the retraction, and it's done.
Yes.
And you define it for every manifold in
Yes.
canonical way. So there's nothing to be proved actually after this.
Yeah,
except that lemma.
Yeah, going from Rn to manifold is fairly
It's a
straightforward.
half-stage event.
No,
Like
okay.
universe, yes, but trust me.
No.
No, we have all these tricks now.
Yeah, I believe that. Yes.
So you just have to.
Right.
The only thing you have to understand are in situations and manifold constructions are canonical.
Yes. Yes. And also the bundle structure over there, so the polyfold bundle is not much. It's very similar to this story.
The constructions are not like in Eliasson that you construct this all kinds of complex. It's just completely trivial stuff.
Yep. All right. Thanks for your attention. I need a beer. It's warm.
We can't do any actual. I mean, just sort of beginning of the black box.
Yes.
For the, even just the Morse. So to show that the Morse, the operator for a gradient for injectors is whatever the words are. I prefer not to do that. Have you got far with that? No. So most of that